Today, we want to do some more approximating of definite integrals, and we're using a limited set of data. So rather than having the whole function where we don't have to approximate, we just find an antiderivative, plug in the endpoints, or just evaluate the function to whatever level of computing power we have. We're going to be looking at a limited set of data. In this case, just 5 values for the function. And yesterday, we did 2 different things. We first did our base model assumption. We just made the function constant on as many subintervals as possible. And then we just put names on these things. So left 4 and right 4. That is using the left endpoint of 4 subintervals. Take our interval from 0 to 12, divide it into 4 intervals with a delta x of 3. And use the left endpoint of each subinterval for the value of the function. So 80, 70, 50, and 20. Those are all on the left of each of those 4 rectangles. Then we also had similarly making the function constant, but using the right endpoint value of the function. So here we're using as much data as possible. Just assuming that the function is constant. Then since we had one value that was an overestimate and the another value that was an underestimate, it makes sense to average those to land on something in the middle. Let's suppose that we needed to give one value, because people don't like ranges of values. They want one value. And if I say it's between 390 and 660, no one would like that. But if I said it was 525, then people would assume that it's exactly 525, because humans are really bad at things like estimation. But it's a natural thing to do. The important thing to recognize is that we change our assumption about the function. Instead of going from just being constant 80 for 3 units or constant 70 for 3 units, we are changing the function from 80 down to 70 in the easiest way possible. That is making a linear function from one endpoint to the next. Specifically, we're making 4 different linear functions, from 80 down to 70, slope of negative 10/3. Then from 70 down to 50 for a slope of negative 20/3. Then from 50 down to 20 with a slope of negative 10. And then from 20 down to negative 10 with once again a slope of negative 10. So it would not be one linear line connecting from 0 to 12. It would be 4 different lines connecting the endpoints. But we're looking at, rather than taking the highest value or just the lowest value, we're taking the average of those 2 values. But in all these cases so far, we are using only the data that we're given. It is not appropriate to use data that we're not given. That's called making stuff up. And if we're going to start making stuff up, we're going to get some bad results. Any questions? My favorite example of making stuff up is there was a study done on whether or not signing an honesty pledge before you did a thing increased your honesty. So like, for example, if I'm giving you a test, like before the test starts, on the front page of the test says, I state your name, attest that I did these problems all on my own. I did not give or receive any help. It's like just essentially like, I didn't cheat on this, and then make you sign it. So they do a study that says that will increase your honesty on whatever comes next. And they studied this by having people report their car data. And I guess they weren't getting the results that they wanted. So they just opened up the spreadsheet and had Excel randomly generate mileages for cars. So it was very obvious for 2 reasons. First of all, they didn't make the font, change the font. So there's like the generated data in one font, the rest of the data in another font. Second of all, if you graph the data, there's a very almost a flat line from people who drove 0 miles per year to people who drove 50,000 miles per year. And then it cut off at 50,000 miles, nothing past that. That's not how people drive. The number of people that drive 10,000 miles per year is going to be way more than the number of people that drive 500 miles per year. And it's going to be way more than the number of people that drive 50,000 miles per year. If you have a big enough sample size like they were claiming that they had, it would be somewhat bell-shaped. A lot of stuff in the average, not very much at the little wings. But they just had Excel generate random numbers. People are really shitty at making approximations. Your ability to predict things is very bad. It gets worse. It gets a little bit worse when you take like one statistics and probability course, because now you know a little bit. And it's like, oh, I know a little bit. And in your mind, it's like, well, now I know a lot of stuff. But then the more you study the subject, it's like, oh, wow, I don't know shit. And this is going to take a lot of time. So most people just kind of like get up to the peak where they feel like they know stuff, and then they just let it go. You know what I mean? Like, think back to the time when you were 14 and you knew everything. Now, imagine, put yourself in the mindset of that 14-year-old and you know everything. Now you look back and you're like, oh, man, what a moron. I didn't know shit when I was 14. But you know more now, but you know that you know less. You perceive that you know less. It's really weird. You're bad at making predictions. That's what I'm saying. You need to understand that. I don't want to go swimming. I might get eaten by a shark because I just saw the movie Jaws. Anyway, what are we talking about? Oh, yes. So in left and right, we're assuming that the function is constant. We change our assumption when we average those two. We are making a linear function from 80 to 70 on the line from 70 to 50 and so on. We're making a linear function. So what we want to do is improve our approximations by reducing the number of rectangles. Now, if we continue this same strategy, the only way to get a better approximation, to reduce our over and under estimates, to get these closer together, the only way to do it is going to be get more data. So we're going to change up the scheme a little bit. I'm going to drop down to 2 subintervals because I'm going to calculate in a different way. So I'm going to do a midpoint approximation. So this is our new approximation technique today, the midpoint approximation. Now, the problem with this particular data set is I've only got 5 points. The sneaky thing is I gave you 5 points so that we could come up with some midpoints. So on our data set, I don't have information about what's going on at the midpoint of 4 intervals. I don't know the midpoint of 0 to 3 or 3 to 6, 6 to 9, or 9 to 12. With 4 rectangles, I don't have midpoint information. So with our particular example, some notes. With n equals 4 rectangles, we don't have midpoint information. With 4 rectangles, we don't have midpoint information. We do not know what's going on at 1.5. If we decide that we're going to make the midpoint of 1.5, the midpoint of 80 and 70, we're just doing the trapezoidal rule. Stop, we're trying to do something new. And you're making stuff up, which is bad. So here's what we're going to do. We're going to reduce the number of rectangles to 2. That's going to increase our delta x to 6, but it's going to give us a midpoint. Not 6 factorial, just 6 exclamation point, because we're surprised that we're reducing the number of rectangles and we should be using an infinite number of rectangles. So I'm going to try not to smear gel. I'm going to go from 0 to 6 and from 6 to 12, and that'll give us 2 rectangles with a delta x of 6. But the advantage that we have here is even though we have 2 rectangles, now I know the midpoints of each rectangle. Now I have a 70 as the middle, and I have 20 as the middle. And I haven't made any data up. I'm using just the data that I have. So the reason that we did this is now we have midpoints. So now we have midpoints. F of 3 is 70 and F of 9 is 20. Let's think about what this looks like, what a picture of this would look like. Made too many marks. Suddenly I tried to make an accurate picture. That's just completely out of my character to make accurate pictures. There's going to be 80. There's going to be 70. 50. So my values are going to be 0, 80. At 3, we're at 70. And then at 6, we're at 50. And then at 9, we're at 20. And then at 12, we're at negative 10. So rather than doing a left all the way across, we're going to take the midpoint. We're going to go from 0 to 6, and then from 6 to 12. We're back to making the function constant on each of these intervals, but I'm going to take the midpoint of each one. And these are the areas that we're going to grab. So notice that this is going to have some over and some under. So instead of being all overestimate, it's going to be some overestimate and some underestimate. rather than all overestimate or all underestimate like we had with left and right, there's going to be some overestimate and some underestimate that's going to cancel out on each rectangle. This is back to a assuming things are constant approach. Also note that we're doing a lot less calculation. Rather than finding the area of 4 rectangles, we're finding the area of 2 rectangles. So our midpoint, mid-2 approximation will be will be the midpoint of 70 and the midpoint of 20, and our delta x is 6. So our delta x is much bigger, but we have our delta x is twice as big, but we have half of the number of entries. So 72 is 9, 6 times 9 is 54. Let's get our other approximation. So I've got a delta x over 2 for the average. We'll have 81s, 250s, and a -10 for our trapezoidal approximation. So it'll be 170 times 3 or 510. We're going to see much worse with left and right. But remember, in this case, left is going to be all overestimate, right is going to be all underestimate. Mid and trap cancel some of that out. Let's see, 8 and 5 is 13. What's 6 13s? 60, 18, 780? I'm doing arithmetic fast, never a good idea. So notice that our difference between left and right is much worse. But notice that the difference we have between the midpoint and the trapezoidal rule is much closer. So the difference between left and right, our range for the actual value went from being between 390 and 660, kind of egregious, to between 240 and 780. That is worse. Your score on this test is somewhere between 50 and 90. Well, that's not helpful. So I go, all right, let me say that your score on this test is somewhere between 30 and 100. It's like, no, 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 that's worse. What we want to notice here is that the midpoint rule and the trapezoidal rule are also going to over and underestimate, but not whether or not based on whether the function is increasing or decreasing like with left and right, but based on the concavity of the function. I didn't prove that. I am just stating it and hoping that you'll all believe me. That's proof by maybe no one will notice. If someone notices, then I can switch to proof by authority. Just trust me, it's true. And if that doesn't work, I can go to proof by intimidation. Listen, you need to believe that this is true right now, or else. That's more proof by threat. There's a lot of discussion about proof by intimidation versus proof by threat. A little bit of gray area. So one of the things that we know is that the actual value of the integral from 0 to 12 of f of x into x will be between 510 and 540. Will be less than 540 and greater than 510. The trapezoidal and midpoint rules will over and underestimate depending on the concavity of the function. Whereas the left and right approximations over or underestimate depending on the direction of the function, the midpoint and trapezoidal rules over or underestimate depending on the concavity of the function. So notice that our function from 80 to 70 to 50, we have a function that is decreasing and concave down. And our midpoint rule was an overestimate. Because since it's concave down, there's like more decrease from the midpoint to the end. That's what concave down is going to do. There's going to be more decrease from the midpoint to the right endpoint. More decrease there. And so that's why we're going to get an overestimate. The other way you could look at it is we could draw a line from 80 to 50. Remember, not 80 to 70, but 80 to 50. And the line from 80 to 50, because the function is concave down, that line is going to pass underneath where the midpoint is, of a concave down function. We draw a line from 80 to 50, that line will pass underneath the midpoint. And so the trapezoidal rule for a concave down function will underestimate the actual area. Any questions? TLDR midpoint rule is a thing. It compares best with the trapezoidal rule, even though they work under different assumptions. Trapezoidal rule is connecting one endpoint to the next with a line. We're assuming the function is linear. The midpoint rule goes back to assuming that the function is constant, but uses the midpoint. Is everybody okay? Now, once again, I just said the midpoint and the trapezoidal rule will show up on opposite sides of the actual value of the definite integral. So you'll probably be thinking, should we average those? And I'm like, oh, yes, we should, but not with equal weights. This raises the question, should we average these two? If they're going to show up on opposite sides of the function, depending on the concavity, or the opposite sides, the actual value of the definite integral, should we average them? And the answer is yes, we should, but not just equally. Simpson's rule is a weighted average of 2 midpoint rules and 1 trapezoidal rule. Simpson noticed when he was doing a bunch of calculations that Simpson's rule was usually about twice as good at estimating as the trapezoidal rule. And so he said, why don't we make a weighted average where the midpoint rule counts twice, since it seems to be stronger. So we're going to do 2 midpoint rules and 1 trapezoidal rule. They both have to have the same number of rectangles. And since there are 3 things involved, we're going to divide by 3. If you write it in single line, you got to write parentheses around the numerator. The interesting thing here is that we are also making an assumption about the function when we do this. The assumption that we're making is that the function is quadratic on each delta x. So in this case, we once again are changing our assumption and we assume that f is quadratic we assume that f is quadratic on each delta x. I'm not going to be able to do this just by looking at it. See, the thing was I was about to, because they're like all 10. I just got to find the middle. It's 40 and a 10. I just got to find the middle, weighted towards the 40. It's going to be 30. And then I'm like, oh, you don't trust yourself to do arithmetic. You're right. So even though we have reduced the number of rectangles, because our technique is more refined, our techniques both the midpoint rule and the trapezoidal rule, each estimation is not just purely over, purely under. Each estimation has a balance between some overestimate and some underestimate that pulls the two approximations closer to the actual value. Now, once again, we could easily build a function with some very poorly chosen, like if the midpoint rule happens to be at a little maximum, and that happens on like all of our little intervals, that would be messed up. But if I did that on a test, that would just be straight up cheating on my part. So here are a bunch of numeric methods for approximating definite integrals based on data. We have our baseline where we have left and right. Then one level up from that, we have midpoint rule and trapezoidal rule. And then one level up from that, we have Simpson's rule, which kind of stands on its own. Whether or not left or right over or underestimates the actual value depends on the direction of the function. Whether or not the midpoint rule and trapezoidal rule over or underestimate the actual definite integral depends on the concavity of the function. Presumably, Simpson's rule would depend on the third derivative of the function. Although that's a bold claim. I wonder if I'm going to back it up or leave it as an exercise to the reader. Any questions? I also like this because it brings up the idea of a weighted average, which we don't talk about, I think, often. How's everybody okay? I took my glasses off, so I can't see anybody's expression. So this way I could just pretend everybody looks happy. If you ever see me walking through the halls and I don't seem to react to your presence or trying to get my attention, I might not, if I'm not wearing my glasses, I might just not be able to see you. So, like if you wave, I'll probably be able to see that, but I won't know that it's directed at me. I don't like to assume that it's directed at me because it might be just waving at someone behind me. So it's like keep on. I thought my vision was really bad. Then one day I accidentally put my wife's contact in. I'm like, oh, wow, did I put both contacts in the same eye? What the heck is going on here? And then I realized I just put her contacts in. I'm like, oh, wow, hon, you are blind as shit. I don't know if you know anybody that's nearsighted, but you can tell they don't have their glasses on because when they're looking at their phone, they're doing this, right? This is where I'm looking at my phone. This is like kind of ridiculously close. With my glasses on, if I wanted to look at it, if I don't have like bifocals, then I have to do something like this to have a chance of reading my phone. Then I saw my wife looking at her phone without her contacts on, and it's like this. Oh, wow. So yeah, I thought I put both contacts in one side, which is actually kind of accurate because I'm at a -3, and her contacts are like a -6. I saw into the past. It's kind of weird. I like put the contact on. I like looked up at the mirror and I saw myself in the past putting the contact on. What was that? So we have these 5 different methods. So the summary goes like this. You'll have some reading with regard to this, but if we want to improve our approximation, the difference between approximations, that's how we can compare, right? If we want to improve this difference, if I want, right now we're like 300 apart, or 200, well, 300 apart. Let's call it 300 apart. If I want to improve that to 30 apart, I have to go from 4 rectangles to 40 rectangles. I need 10 times the number of calculations to get 1 decimal place of improvement. If I want to bring my midpoint and trapezoidal rules closer together, if I do 10 times the number of rectangles, if I go from 2 to 20, that'll get an improvement of 2 decimal places. So if I had 20 rectangles, which would be similar to the amount of data up here, if I go to 20 rectangles, then instead of being hundreds of parts, they go to tens to what units apart. So a difference of 300 drops to a difference of 3. That's how much more efficient the midpoint trapezoidal rules are, because we've got some over and underestimate canceling out at each rectangle. Simpson's rule improves if we do 10 times the number of rectangles. So from 2 to 20 rectangles. Simpson's rule improves 4 decimal places. So that's the strength going up. We go from 1 to 1, 10 times the calculations for 1 decimal place, to 10 times the calculations for 2 decimal places, to 10 times the calculations for 4 decimal places. Other things that we want to understand, left, right, and midpoint rule are all assuming that the function is constant. The trapezoidal rule assumes the function is linear, and Simpson's rule assumes the function is quadratic. So presumably there's something else out there. Maybe there's another Simpson, something Simpson-like, that we could make some other weighted average, and we would assume that the function is cubic on each. Subinterval. Any questions? How's everybody think? All right. That's our thing about approximating definite integrals. These are some formal methods for approximating definite integrals. It's what we can do if we have a limited set of data rather than an actual explicit function. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.